I got this comment and I thought, I don't like entropy. But why? Apparently it is
one of the most important concepts in all of physics.
The concept that's crucial to chemistry and physics. It helps explain why cream spreads in coffee.
Or why the world tends towards chaos. It's related to energy and it's even
defining the arrow of time, predicting the ultimate heat death of the universe, and providing the driving force for the development of structure as well as decay.
So it may
even be the reason that life exists.
Isn't that astonishing? Yep, and that's exactly my point. I mean, come on. That feels like a lot, and all this should come from only one concept? But am I onto something here, or have I just not understood entropy? I mean, there are a lot of possible misunderstandings about entropy. Like, these have different entropy because chaos means high entropy and order means low entropy. Things go from order to disordered. It is forbidden for the total entropy to decrease. Entropy is energy. Entropy gives us the era of time. The universe will end in a heat death. Entropy is complexity. Which of these are true, which are false, and which are completely misleading? We debunk them all, while we approach the maybe greatest misunderstanding, that entropy is the biggest concept in physics. We will understand what entropy actually is in a moment. Spoiler, it's not order or disorder. But first, where does the idea that all this is linked to entropy come from? From the second law of thermodynamics, which is, by the way, an empirical law. Put simply, empirical law means we see something consistently happening in the same way and conclude that this is how it works. So it's not derived mathematically from fundamental principles. Empirical methods are a great way of doing science, don't get me wrong. But the fact that this law is empirical makes me even more skeptical about the increase of entropy having such a huge fundamental impact. What is the second law about? It's about waste heat or about inefficiency of things like fridges or engines. A machine will never be perfect, but will generate some unwanted heat. A fridge cools things down, but actually expels even more heat out the back. The more heat is generated, the more entropy is generated as well. So you can think of entropy as being a way of measuring the inefficiency of machines. You can think of it this way, just like people from the age of steam engines did. Then the second law of thermodynamics also makes sense. It says that the total entropy can only stay the same or increase over time. The heat out the back won't suddenly disappear. But this doesn't help much beyond fridges or steam engines. At least, in my opinion. I mean, what does this have to do with mixing coffee and cream? Luckily, Boltzmann's view on entropy is more precise and more interesting. It will help us to better understand the second law of thermodynamics. So what actually is entropy? Gas in a closed box is a common example when talking about entropy. And it's an example where one of the biggest misunderstandings about entropy comes from. That chaos means high entropy and order means low entropy. Which of those two boxes has a higher entropy? If you think low entropy means order and high entropy means chaos, you would probably answer this. But if we just look at those two special configurations of gas, they have the same entropy. Both have entropy 0. These two specific arrangements of the gas atoms are called states of the system. In physics, a system is simply the part of the world we are currently studying. Here, the box with gas. All current positions of atoms make up the current state of this system. So, those are two possible states. Now, entropy is related to the number of states that give you the same appearance. Only this state looks like this state. So the entropy of both only depends on one state. And the entropy of a single specific state is 0. They have the same entropy. Entropy is only above 0 if more states give you the same appearance. But at this level, this doesn't make much sense. But entropy becomes useful if we switch our perspective from exact positions of atoms to overall appearance. If we look at coffee mixed with cream, we could look at each individual molecule, but we can also look at the overall appearance. There are a lot of different arrangements of molecules in coffee with cream that make it look mixed, but only a few that make it look separated. Now, one specific arrangement of molecules is one specific state of the system, and the entropy of the system is given by the number of different states that give us the same overall appearance. That's why mixed coffee with cream has a high entropy, because there are a lot of possible states or configurations of molecules that make it look mixed. In contrast, there are only very few ways the molecules can arrange so that coffee and milk stay separate, so this has low entropy. Okay, so entropy is high if there are a lot of possible states that give you the same overall appearance. This may look like chaos, but that's not why it has high entropy. It has high entropy because it has a lot of possible molecular arrangements. To be precise, entropy is proportional to the logarithm of the number of different states. But that's just a mathematical detail. It explains why those single states have entropy 0, because the logarithm of 1 is 0. For the gas in the box example, you could say that the overall appearance you are interested in is how many atoms are on the left and how many are on the right. Then you could list all possible states that lead to the same numbers on the right and on the left. You would find that a smoothly distributed gas has the highest number of possible states and therefore the highest entropy. So, if someone says to you that this has higher entropy than that, you can now show off and say that this is only true if we are talking about the overall appearance of the gas and not about its specific microscopic states. And this is something that annoys me about entropy, that it kinda depends on perspective. I mean, the atoms don't care if we look at their macroscopic or microscopic appearance. They don't care if we think this looks like order and this like chaos. That's why I believe the terms order and chaos are not the best way to talk about entropy. Furthermore, they are pretty misleading. Sure, coffee and milk always mix, which looks like chaos. But chaos is not the reason. The reason lies in the microscopic world of atoms. Atoms or molecules are arranged in a certain way, and from there they can evolve into other possible future arrangements. They can evolve into each of those states, let's say with the same probability. Each possible future state belongs to a certain overall appearance. More belong to an arrangement looking like smoothly distributed gas or mixed coffee and cream. Why? Because overall, in total, there are simply more possible states that look like this to us. So, if the gas now goes from its current state into a future state, it's more likely to go into a state that we associate with high entropy. The atoms could go into every possible state, but they are more likely to go into one of those states that we group together into the biggest group. So, instead of thinking of higher entropy as less order, I like to think of it as just higher probability. An increase in entropy is simply the most probable outcome. Great! Now we've linked entropy with probability, so we can state that higher entropy is more likely. Wow! Thanks, Captain Obvious. So, things don't essentially go from order to disordered, they go to more likely, where more likely arises out of more possibilities. I think unlikely states seem so special for us that we label them as ordered. So if you use the words order and chaos here, keep the statistical background in mind. In reality, way more states fall into the high entropy group. So many that it's really unlikely to decrease entropy. So unlikely that it's practically not happening. That's why the second law of thermodynamics says it is forbidden for the total entropy to decrease. But is this true? Remember that I said that this law is empirical? This means we just never saw the entropy of a closed system decrease. And that's why the second law of thermodynamics states that. We strongly believe that it is true. But who knows? Maybe this is more like a no girls allowed in the treehouse rule, which isn't a rule but just something that keeps happening. However, it is probably not the end of the story. What I mean is that entropy is an emergent concept, not a fundamental one. Maybe that's why I don't like it. I mean, physics usually spoils me with how fundamental it is. If I've spoiled you with a great video so far, please leave me a like and subscribe. Thanks. Okay, but isn't entropy that amazing thing that's giving us the arrow of time? Before we talk about that, let's link the two descriptions of entropy. Low entropy could look like this, and it's associated with useful energy. The gas atoms, for example, could push something while they spread out. Over time, As entropy increases, all the energy is eventually transformed into waste heat. Evenly spread out atoms cannot push anything, and the heat coming out of your refrigerator is basically useless. So, you can also think of entropy as a measure of how spread out energy is. Concentrated energy has few states, low entropy, and is therefore pretty usable. Spread out energy has many states and high entropy. At maximal entropy, energy is completely spread out and completely useless. By the way, that's what we call an equilibrium. So, entropy is not the same as energy. Energy is conserved. Entropy is statistical and can increase. Entropy measures how energy is distributed, but not the energy itself. Okay, back to the era of time. Given the second law of thermodynamics, it makes sense that the universe will have a higher entropy tomorrow than it has today, and an even higher entropy the day after tomorrow. And finally, at its end, it will have reached maximum entropy. The universe will be structureless. No stars or galaxies remain. Matter is extremely sparse. Energy is maximally spread out and useless. This is often called the heat death of the universe. A pretty shitty choice of name, because apart from being empty and smooth, it will be really cold. Why was it called like that? This comes from the description of entropy when it was linked to waste heat. So yes, according to the second law of thermodynamics, the universe will end in a heat death. But this does not mean at all that it's gonna be hot. So, it makes sense that the universe will have a higher entropy tomorrow than today, just because there are more possible states. The thing is that the fundamental laws of physics don't distinguish between tomorrow or yesterday. That's exactly why everyone gets so excited about entropy giving time a direction. If physics allows atoms to rearrange in a certain way, it also allows them to just have been arranged that way. So, if our reasoning predicts entropy to be higher tomorrow, it should also predict that it was higher yesterday. So the question is not why coffee and cream never unmix, that's forbidden by the second law. The question is why coffee and cream were unmixed in the past. And here comes the past hypothesis to save the day. The past hypothesis is the simple assumption that the universe started off with extremely low entropy. With this assumption, it makes sense that entropy was lower yesterday, because it was even lower the day before yesterday. So, this is where the error of time comes from. Actually, not directly from increasing entropy, but rather from special conditions in the early universe combined with increasing entropy. Why was the early universe in a state that had low entropy? We'll see in a moment why these conditions are low entropy. But how did they come about? If you know this, leave me a comment, otherwise I'm afraid we don't know this yet. But we know that life feeds on low entropy. And this brings us to the last misunderstanding, that low entropy equals complexity. Sure, whether it's coffee with milk or the end of the universe, both look pretty boringly uniform, simple and not complex. But the early universe was also just a smooth soup, simple and not complex. But why do we say that entropy was low? Because of gravity. With gravity, typical arrangements are more clumpy and not smooth. Matter in the early universe was pretty dense, so it was extremely unlikely to have a smooth distribution. There were only a few possible states. As the universe expanded, gravity clumped matter together and entropy increased. It's actually not the low entropy or high entropy states that give us the most complexity, but the states in between. I mean, look at the pattern milk forms as it mixes into coffee. A human being has pretty low entropy, but not because it is complex. No need to take this personally, it has low entropy because it is such a special state. Only a few possible microstates form that. But how can this even occur in a universe where entropy increases? To maintain this special configuration, life must increase surrounding entropy. So the connection between life and entropy is not complexity, but that life feeds on low entropy. Where does the Earth get low entropy from? The Sun. The Sun's radiation has low entropy because its energy is concentrated in only a few photons. The Earth absorbs the sunlight. Energy cannot be lost, so the Earth also radiates. But the energy of that radiation is spread out over a much larger number of low-energy photons. Or put differently, we're back at the waste heat. So, the Earth is like a huge fridge that decreases entropy inside but increases total entropy even more. Okay, this was a lot. Most importantly, we learned that things evolve toward their most likely appearance. Something is more likely if there are more possible underlying states. And that's essentially what we call increasing entropy. So, digging into entropy was more exciting than I thought it was going to be, but I admire physics for its fundamental ideas. Sure, outside of physics you are often dealing with non-fundamental descriptions of reality. But how useful is that? I mean, modern medicine more useful than particle colliders? Come on! Okay, please don't hate me in the comments. Hey, we got the error of time by combining an empirical law with an assumption. Okay, what might not fully satisfy me is still the best explanation we currently have. And yes, it may be obvious to state that the universe evolves into what it is most likely to evolve into. But we should definitely state the obvious. I think that's even the first thing we should do in science. So, even though I'm still not friends with entropy, and I don't think it's the biggest concept in physics, my respect for it has grown a bit. I mean, without low entropy near the Big Bang, we wouldn't be here. By the way, did you know that the Big Bang is not the beginning of the universe? Check out this video for more. Thanks for watching. Have a great day.